Hiya. So, branching out from the A level, as you can probably tell, this is a lesson covering 4.7 organic chemistry as part of the AQA GCSE single science specification. So we're going to go through all of the organic chemistry. We'll start with the very beginning. We'll start looking at the structure of carbon and the bonding that it undertakes, and then we will move into things like fractional distillation. We'll go over the alcohols, carboxylic acids, esterification and polymerization towards the end. Can't tell you how long it's going to be because obviously I'm at the beginning. Hopefully not too long, but there is quite a lot, so I don't know, we'll see. So to begin with, we need to realise what carbon looks like. So on the periodic table, it's carbon, and there's a 12 and a 6. And in terms of atom structure, this means that we have got a nucleus. I'm just going to draw that as a solid circle. Show that in. Made of 6 protons, 6 neutrons, and then around the outside we have got 6 electrons. And we know, oh that's horrible, that the first layer or the first shell has always got 2 electrons in it, and that gives us 4 on the outside. Okay, now that 4 on the outside, and I'll put a little note in here in a different colour. 4 electrons on the outer shell means that we need 4 more electrons to reach a full stable outer shell. This is important when we come to look at the bonding in the alkanes and the alkenes and how they react. So let's get started straight into it. We're going to start by looking at crude oil. Okay, so crude oil is originally a fossil fuel. It's found underground, and that means that it's made of the remnants of lots of dinosaurs and ancient plants and things like that that have decayed and been buried underground under the lots of sediment and layers of rock over time, and that pressurized them and has resulted in the formation of a liquid that is crude oil. And crude oil itself is a mixture of hydrocarbons, and as you can see just below, it says that hydrocarbons are compounds that contain only hydrogen and carbon, and they are bonded together. So that means that in terms of our structures, hydrocarbons should only have CH bonds and CC bonds. And most of the hydrocarbons that we find in crude oil, that fossil fuel, are something called alkanes. And let's have a look at what they are. So these alkanes, as we've said, are a type of hydrocarbon. They're only carbon and hydrogen stuck together. And they form straight chain molecules. And they've got what we call single bonds. So that means that between every C, there's only a single line. And that single line represents a single shared pair of electrons. Okay, so if we look at it in terms of our outer shells, for this first carbon, we can have 4 crosses, and then we've got the overlapping of the shell with another carbon. Notice I'm using dots and crosses as well. So that single line actually means this bit. Okay, so alkanes are, as we've said, straight chains, so we can have lots and lots of these carbons sharing their outer shell, and they've got a general formula. Now in chemistry, a general formula is the way that we can quickly figure out the chemical formula for a molecule. And the general formula for alkanes is CnH2n plus 2. Okay, and this is a horrible way to write it. The superscript doesn't seem to have worked. So CnH2n plus 2. And as it says there, that means for every carbon, so whatever n number of carbons, there are double plus 2 hydrogens. Okay, so if I've got C6, for example, my H I know is going to be 2 times 6 plus 2. So actually my chemical formula for this molecule is C6H14. Okay. Now when we're drawing alkanes, first thing we do is we draw a number of C's connected with those single lines, those straight chains, for however many C's are in the molecule. Okay, so if it says C4, just bung them all in a strip. You'd go C, C, C. Now stick one over there. Then you have to add in the hydrogens around it, because we know that they're a hydrocarbon, so they've only got C's and H's. And we know because that carbon has got 4 electrons on the outer shell, it needs to have 4 bonds. Okay, so we can have 4E- on outer shell. And all we've got to do is add those in. So be careful about these. On the ends, there are 3 hydrogens. Okay, so you can see that they've got 4 bonds around each of them, and I'll just show you what I mean by the 4 bonds. We'll count them up. So there's 1 there, 2, 3, 4, and this one on the far right side has got 1, 2, 3, 4. Now the ones in the middle are a little bit different because they've already got 2 bonds. So I'll write those in again. 1, 2, 4, this one, and then we've got another 1, 2, 4, this one. So those 2 central carbons only need H's above and below. Okay, and then just to figure out what the chemical formula is, I count my number of N's, so I've got 4 there, and then I go around and I count my H's. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So H10. Don't forget when you're writing this, the numbers go below and they're subscript, so they're slightly smaller and just drop below. We're not writing them like C squared or anything like that. And if we're not too sure, we can double check that our chemical formula that we've thought of, the one with the question mark next to it, double check it using our general formula. So C, if N is 4, H 2N plus 2, so 2 times 4 plus 2 is 10. Perfect. Got that right, smashing. Now for all of these organic molecules, there's a few prefixes that we need to know. Okay, and that's on this table over here. So if you see meth at the beginning, M-E-T-H, that means that the molecule has got 1 carbon in it. Eth is for 2, prop for 3, bute for 4, and then onwards from 4, they sort of follow the same prefixes that you get in your polygons in maths. So a pentagon, hexagon, heptagon, octagon, nonagon, decagon. Have a go, you can pause now, at drawing what ethane looks like and octane looks like. And then if you would like to, have a go at drawing what would happen if you had decane and you removed the formula for butane from it. So you can pause now, have a go at that, and then I'm going to put some pictures on the next few slides to double check where you are. So ethane looks like this, and as you can see, I've got my eth prefix, which I know means that I'm going to have 2 carbons. So ethane has 1, 2 carbons joined together by a C-C bond, so a single bond, and then around it, I've got to make sure that each of those carbons has 4 bonds. So my chemical formula for ethane is C2H6. Octane is exactly the same. I know that oct, like an octagon, is, or an octopus even, has 8 carbons. So I draw those all in a chain, and then I attach all of those carbons around the outside. And again, we should have C8H18. Finally, if you've got decane and you take away butane, so dec is 10, but is 4, you end up with hexane, and that looks like this molecule. Hex, like a hexagon, is C6H14. Okay, so if you're not too sure, maybe have a go at writing out all of the chemical formula for these. So methane, for example, would be CH4, because that's N is 1 and 2N plus 2 is 4. Okay, you can have a go going down all of those if you would like. You're welcome to ask me if you're correct as well, if you need to. Now, sometimes we want to separate crude oil. We know that crude oil is a big old mixture. We've said that it's a mixture of those hydrocarbons, so you could have some decane in there, you could have some methane in there, and sometimes we just want to separate them so we can effectively bottle them up. Now, the way that we do this is through something called fractional distillation, and we use this using a fractional distillator or a fractionating column. And I'll show you a picture of that on the next slide. Now for fractional distillation, what we do is we evaporate our oil and we condense the vapours. Now, evaporation, just as a reminder, is when we go from a liquid to a gas, and condensing is when we go from a gas to a liquid. And depending on the hydrocarbon determines at what temperature it will condense at. And that's the whole premise surrounding these fractional distillating columns. And each fraction, which is what we call the sort of splits on the column, or splits on the apparatus, is going to have similar carbon chains around them. So I'll explain on the next slide, it'll probably make a little bit more sense. Let's have a look at it then. So this is your apparatus. In an exam, they love giving you diagrams like this. So what we can see here is we've got crude oil being pumped in, and this is our mixture of liquids. We're going to have a big old flame at the bottom, heating it up. And you've got to be aware that if you're asked to draw and label the apparatus, you need to draw that heat source in. And that crude oil is going to heat up and slowly evaporate. Okay. Now, the shorter the molecule, the lower the boiling point. And you can see that up here. So these molecules, the ones that you find at the very top, have got the lowest boiling point. And that's because they've got the weakest intermolecular forces. And if you think back to when you've done things like specific latent heat and things like that, you know that the lower the energy needed to separate the molecules, the easier they are to change state. So these short molecules don't have a lot of strength in terms of holding on to each other. And that means that they're able to evaporate really quickly, and they condense at cool temperatures. Conversely, the big heavy hydrocarbon molecules are found at the bottom of the fractionating column. I'll just write that here. This piece of equipment, fractionating column. And as I said, those big molecules, those long chains, decanes and even bigger, are going to have a really high boiling point. And that means that it takes a lot of energy for them to change state. And as you can see here, actually we don't get the bottom fractions turning into a gas. Instead, they just sort of use gravity to tap them off of the bottom, things like bitumen. Other things that we can see here and patterns that we have to be able to mention, especially for an exam when it says about, describe how a fractionating column works or describe the process of fractional distillation, you need to say that the boiling point decreases as you go up the column. Okay, and also boiling point, I'm just going to write BP, decreases with shorter chain lengths. Okay, so that means, and this is just summarising everything that we've done, that means that it requires less energy. Or lower temperatures. Okay. We can see a few other keywords on this sheet. So if you did want to pause this video now and make some notes, absolutely fine. You can print screen, absolutely fine. We can also see on the fractional distillating column or the distillation apparatus a few other words, as I said, things like volatility and viscosity. Okay, so viscosity is how runny things are, so how liquidy, how fluid, how easily they move from place to place. And what we can see in this fractionating column is that actually the shorter the chain length, the less viscous the molecule is, or the less viscous the substance is. And you can tell that from the fact that at the top of the column, where the shortest chains are, they're actually a gas, like a gas state. And then the next chain down, gasoline, that's really liquid. You know that you can pour gasoline. You see it in the music videos, you know, the Eminem and the Rihanna one. At the bottom, though, where we've got things like bitumen, for roads and roofs, that's going to be things like the stuff that makes tarmac. It's really claggy. So this stuff at the bottom is very viscous. Very, very thick. A bit like running through like Play-Doh and sand all mixed together to make a horrible soup. We've also got to consider the volatility or the flammability of each of those fractions as well. So the top molecules, the shorter molecules, are more volatile. So they've got a higher flammability. And this is why they're generally used for fuels. Whereas when you go towards the bottom, things like bitumen, they are not very volatile. They are less flammable. And in turn, they're quite resistant to heat. So they're used for more structural things like roads and roofing. We can summarise the properties of the hydrocarbons like this. So the low boiling point fractions are found at the top of the column. And these are the molecules that are small, short chains. In terms of colour, they're colourless. We know that they're a gas, or they're something like gasoline, so they're quite light. We know that they're not very viscous. In fact, they're quite runny. They're either a gas or a very watery liquid. And they are very, very easy to burn. They light easily. And they burn with a clean flame, and that means that they're not smoky. So they combust really readily. Medium boiling points, sort of the middle of the column, are medium chain lengths, maybe five or more carbon molecules. They're slightly more yellow, and they become slightly thicker as well. So the longer the chains, the thicker they are, because the chains can sort of interlink a little bit more. Like if you link your fingers together, that's what the chains start to do, and they start to not be able to slide over each other as effectively. And because they're thicker, they're harder to light. They don't separate and combust as efficiently, and therefore we get some smoke which is caused by incomplete combustion. And then finally, with those high boiling points, they are found at the bottom of the fractionating column. And as we've said, they have got long chains of hydrocarbons, or they've got long carbon chains actually, so they're like C10 plus. And actually colour-wise, they're very, very dark, and they're thick as well. They're like honey. Really sticky, really thick, really difficult to do anything with. And in terms of difficulty to do stuff with them, they're really difficult to light. So we saw at the bottom, we've got that bitumen stuff. That's going to be used for roads and for roofing, especially if you've got an extension. And therefore, they're not really used as fuels. So now it's your turn. This is a 3-mark exam question. I'd like you to pause if you're using this as a revision resource and have a go at this question. Diesel is separated from crude oil by fractional distillation. Describe the steps involved in the fractional distillation of crude oil. It's 3 marks, as you can see at the bottom. So give yourself about 3 minutes and then play this video again when you're done. So the first mark is to say that you need to heat the crude oil to vaporise it. And vaporise means to start turning into a gas. If you remember, there was the specific latent heat of vaporization. That's what we're looking at. We're looking to see how much energy is needed to turn them into a gas. Then what we need to mention is that the vapours condense, and they condense at different temperatures because they've got the different boiling points. Now remember, condensing is when they turn from a gas to a liquid, and this is then where we get the fractions coming off of that column. And they occur at different temperatures because they've got those different chain lengths, but it's not asking me about why. Okay, it's only describing the steps involved. So heat to vaporise, the vapours then condense, and they condense at different temperatures. If you didn't get any of those points, pause, make a note of them, make a little star shooty thing around the outside of them so it's really, really flagged up, because again, much like when we've said about survive, reproduce and pass on the genes to offspring as the holy trinity of evolution, vaporize, condense and at different temperatures is like the holy trinity for fractional distillation. And here we go, there's a nice little summary diagram for you. You can take a photo of this, you can leave this here and pause and then print it out if you want to, if you wanted to have that diagram for you guys to label as well. Now, these hydrocarbons, as we've said, are generally used as fuels. So when we're talking about combustion, what we're actually talking about is reacting with oxygen. And that oxygen comes from the air. So combustion won't happen in a vacuum. And really what we've got happening is two different types of reaction. We've got complete combustion when there is enough oxygen for the fuel to react. And incomplete combustion where there isn't enough oxygen. And you can see there that we have got two different reactions happening. So in complete combustion, a fuel and oxygen will react to form carbon dioxide and water. Whereas in incomplete combustion, the fuel, and they'll tell you what fuel it is, with oxygen reacts to form carbon monoxide, mono meaning one. So there's only one oxygen there. Notice there's not that little two, plus carbon and water. So now we're going to have a look at a few examples and see how we write those out in chemical formulae. Now it's your turn to have a go. I'd like you please to write out the combustion equations, both complete and incomplete, for methane, propane and butane. And remember, these are not written properly because this program doesn't like when I put the superscript and the subscript in, so I'll just write them properly for you again. So pause, spend a couple of minutes having a go at these, and then play again when you're ready. I'd like the chemical equations, not the word equations. So you should be using the formulae, not words. So we're going to have a look at these two equations in two different colours. I'm going to do complete in blue and then incomplete in another colour. I haven't decided yet. So methane, CH4 plus 2 O2 gives us CO2 and 2 H2O. And then incomplete combustion we're going to do in red, just at the top. Our equation is 4CH4 plus 5O2 gives us 2 carbon monoxides plus 8 lots of water plus that carbon at the end. Now notice that we can't cancel that down any further because that oxygen has got that really awkward 5 attached to it. Now let's take a look at propane. So complete combustion where we've got enough oxygen, maybe we've got an open fire for example, C3H8 plus 5O2 gives us 3 CO2 plus 4 H2O. And then incomplete combustion, maybe we've not got enough oxygen for whatever reason, perhaps where the burning is happening is in an enclosed space. For example, we're going to have 2 lots of propane reacting with 7 oxygens, and that's going to give us 2 lots of carbon monoxide again, and we are going to get 8 lots of water, and we're going to get also some carbon dioxide, and we're also going to end up with some carbon. And then finally butane. So butane, as we know, is C4H10, and this one's a little bit trickier because it requires 2 lots of that butane and 13 lots of oxygen to make 8 carbon dioxide and 10 lots of water. Now for the incomplete combustion, I'm going to leave that blank. I'd like you to email me with what you think the answer is, and I'll let you know if you're right or wrong. Now here's another little task for you guys to do by yourselves, a little pit stop. Have a go answering these questions. You can pause, do them in full sentences, work with each other, maybe be on a call together and see how you feel about them, and then play again when you're ready to go through the answers. So for the first one, what is fractional distillation used for and how does it work? Fractional distillation is used to separate crude oil. Okay, so the hydrocarbon mixture in crude oil is separated into fractions. It works because each fraction has a different boiling point and condenses at different temperatures. And remember, it's that condensing that is key to the idea of fractional distillation. Just because it boils at a different point means nothing unless they condense back into the liquid and we can tap them off again. A fraction is a small mixture of hydrocarbons. And in that smaller mixture, we've got a narrower range of hydrocarbon lengths, and they've all got similar boiling points. So again, they all get tapped off at the same kind of level. The formula for the alkane with 5 carbons, with using our CnH2n plus 2, is C5H12, and hopefully you will know by now that that is obviously not written in the way that it should be, C5H12 like that, and actually that is pentane. Now for question 4a and b, as we increase the carbon length, the flammability decreases. That means that we need a higher temperature to start them burning. If you think about things down at the bottom, like bitumen and the stuff that's used for like roads, tarmacking and things like that, it would be awful if they had a really low burning point, really low flammability, because they'd be setting on fire every time the weather was a little bit warm. For boiling point as well, they increase, so the boiling point is higher and harder to boil. They're also going to condense at higher temperatures as well. And when a hydrocarbon burns, what are the two gaseous or gaseous products? So those are the products that are in the gas state, and we've got carbon dioxide, CO2 and water in terms of vapour. And in an exam, remember, if we're doing the state symbols, especially if we're looking at combustion, it needs to be H2O gas, that little g in the brackets afterwards. So now we're going to have a look at what happens if we want to take a big hydrocarbon molecule and we want to break it down a little bit smaller to something that's a bit more usable. And this process is called cracking, and the definition is at the top there for you. So a large hydrocarbon molecule is heated in the presence of a catalyst to break it down into smaller molecules. And this catalyst is used to reduce the activation energy. Remember that activation energy is the energy needed to start a reaction, and therefore it's going to increase the speed of the reaction. So this process using a catalyst is going to be quicker and also less energy intensive, which is generally quite a good thing because it costs less money. Now the smaller molecules can actually be either short chain alkanes, so we get maybe from C4H10, maybe we're going to break it down into 2 lots of C2H5, that ethane, for example. But we can also produce something called alkenes, and they're slightly different. And these alkenes can go on to make something called a polymer, which we'll look at a little bit later on. So the way that we do cracking is a thermal decomposition process, and that means that we're going to use heat to break down the molecule. So we're going to apply heat in the presence of a catalyst, and then we're going to remove the products that we produce. So the first thing we do is we're going to heat the hydrocarbons to vaporize them. They're now in the gaseous state, so maybe we're C4H10 gas, for example, and then we're going to pass that paper in a little tube over the catalyst. And the catalyst might be attached to a metal grid, it might be beads, it might be a powder. And remember, sometimes in the exam they might try and trip you up and say, oh, why is it better to use powdered catalyst versus big solid lumps? And you'd need to talk about something about like surface area, things like that. And that catalyst, as we've said already, is going to speed up the reaction. So here we can see the apparatus for cracking. I'll zoom out a little bit there. You need to be able to recognise and draw this setup. And as you can see at the end of my little boiling tube, I've got paraffin, which is going to be my source of hydrocarbons, and that's soaked into a fibre, a non-flammable fibre, something like a ceramic. And I'm going to pass the fumes or the vapour caused by heating that up over aluminium oxide granules. And that aluminium oxide granules are acting as our catalyst. Where it says clamp here, that's obviously just where I'm going to hold the apparatus, and then I've got this little tube to connect the products over here to the heated tube over there. So spend a couple of minutes drawing it out. I'm going to ask you to do some sorting of statements in a second. So hopefully this diagram should make a little bit more sense if you don't know what's going on right now. So hopefully now you have a lovely diagram of the cracking apparatus. These statements are not in the right order. So what I need you to do is organise these bullet points 1, 2, 3, 4, 5, 6 into the correct order, and then use them to label your diagram to give you that process and how cracking actually happens in the lab. So you can pause and then play again when you're ready to go through the right order. And then I don't have a labelled picture of the apparatus, unfortunately, but you surely, hopefully get the gist. So to begin with, we've got those large molecules from the ceramic fibres that's soaked in the paraffin passing into the cracking chamber. And these are now moving as vapours. They've been heated up, they're in the gaseous state, and they're going to pass over the aluminium oxide. If we recall, that's our catalyst. That's going to facilitate the cracking, means that it's going to speed it up, reduce the energy, and the products that we've made, those large molecules, are now breaking up into the small molecules. And these small molecules can move out of that tube, and they can go into a distillation column. So what that means is that they're going to become smaller and they can condense at a lower temperature. And that means that they're going to be able to be separated in their fractions depending on the temperature of the column. And we can keep heating our hydrocarbon source, our paraffin for example, until all of the fractions have been distilled and boiled away. Now we've spent some time discussing alkanes and we've mentioned alkenes, but we haven't actually spoken through what they are. And the alkenes are what we call an unsaturated hydrocarbon. This means that they've got a carbon-carbon double bond, which we draw as sort of like an equal sign between the two carbons. And the general formula for these alkenes is CnH2n. With alkanes, you add. So that's a nice way to remember it. Alkanes, you add 2 to the H2n. Whereas for alkenes, you don't. Another way I like to remember it is that alkenes, if you were to write them as capitals, the E's you have to draw with an equal sign to make the E itself. Okay, and it's like the carbon double bond. Completely fine if you want to ignore me with that. You figure out your own way to remember it. But alkenes have got that carbon-carbon double bond, and alkanes have only got single bonds. So for our alkenes, for every carbon, you double it to find the number of hydrogens. And I want you to have a go at filling out this table. Research what each of those alkenes looks like. So ethene, propene, and butene. And I've given you random bits of information for each of them. You just need to figure out. So for carbon and hydrogen, I'm talking about how many. You're going to need to use the formula for that. Same for the chemical formula. Remember to write it slightly lower. And then for the diagrams, you're going to have to do some Googling, maybe use your knowledge. Okay, so pause and then play again when you're ready to go through the answers. So hopefully your table should start looking a little bit like mine. So ethene is C2H4, and we just draw it simply like this. Remember that our carbons only have 4 bonds, and this double bond in the middle counts as 2. So between the carbons that have got a double bond, you can only put 2 other bonds around them, okay, not 4. Propene has got 3 carbons and 6 hydrogens, and I'll just draw it up here for you. I'll swizzle across a little bit actually. So C, double C, and then a single C by itself. We don't put more than 1 double bond in, that makes it a different molecule. So I go round, I know that if I've got a single bond, I can add 3 extras around, so that's CH3 over there. And then this carbon in the middle is a little bit tricky because it's got 2 here and 1 there, which means I can only add 1 hydrogen to that carbon. And I know it looks a little bit odd, that's absolutely fine. And then finally on this last carbon, I can add 2 more hydrogens. And finally, for butene, that's C4H8. And if you weren't too sure, you could have just counted up all of the carbons and the hydrogens that are in that picture. Now, we've mentioned in the previous slide about the word unsaturated, and in an exam you've got to be able to use them. So saturated means that all of the bonds in the carbon are used up on different molecules. So it could be that there's attached to 4 different hydrogens, but they're 4 different hydrogens. They're not the same hydrogen twice. Okay, so saturated is for single bonds. Unsaturated is when you've got double bonds. So we say that our alkanes, such as propane, are saturated, whereas propene has got that double bond, unsaturated. Make sure, if you're not too sure about those keywords, you write them down now, because you need to be able to apply them in an exam situation. Now, sometimes in an exam they might be really annoying and give you a cracking reaction, not like a really good, like, oh, that's cracking, just a reaction involving this catalytic cracking, and ask you to give the product. Okay, so when we're talking about cracking reactions, the number of carbons in the products, if I just go back and I'll actually get my pen, in the products has to be the same as the number of carbons in the reactant. So have a think, have a go. What products in alkanes and alkenes could you make from decane, this big old hydrocarbon, C10H22, down the bottom? Have a go at writing them out. You should definitely have at least 3, if not more. So pause and play again when you're ready. So one of your answers might have been that we can take decane, C10H22, and we could break it down to octane, C8H18, and ethene. Okay, remember I said you can separate it into alkanes and alkenes. And now ethene, we're going to talk about this polymerization in a second, is reactive. That double bond means that it can undergo different chemical reactions and be used to make something called a polymer. Remember that ethene is unsaturated, it's got that carbon-carbon double bond, whereas octane is a saturated hydrocarbon. All of those carbons are attached to 4 different molecules. So again, we've got this table for you guys to fill out. So using what you know, can you complete the table to draw and name the products of cracking in each long chain hydrocarbon? So have a go. I've given you most of the information. You just need to draw lots of them. Maybe do a little bit of maths for the second one. Figure out what goes over here in the 3rd row. And then for the 4th one, up to you what products you produce. So use each row to then write a balanced equation for the cracking of each reactant. And what I mean by that is, if you think back to the last example, that means that I've got C10H22, and that's going to break down, no reactants, no oxygens reacting with it or anything like that, into octane, C8H18, and ethene, C2H4. So pause, draw the table out, do the equations. It should take you about 5 minutes, if not a little bit longer to do. Make sure it's neat. Check that your alkenes have got that double bond, but only one of them. And then play again when you're ready to check the answers. So your table should look a little bit like this. I recognise this is a little bit ugly, but what can you do? You know, I've tried. Bear with me, I've tried. So for each of the products or reactants that I didn't give you, I've given you the chemical formula with them as well. Hexane is C6H14, butane C4H10, octane C8H18 as we've said, and then ethene C2H4, propene is C3H6, and butene is C4 H8. Whoop, made a mistake. Now for your balanced equations, the pictures are going to stay on, don't worry. They should look a little bit like this. So again, as you can see, where those boxes are is the arrows. All of those numbers should be subscript, so a little bit smaller and lower, but hopefully that was fairly straightforward. If you're still struggling, ping me an email. We can go through this together, maybe in some free time after school or before school, whenever. Now we're going to have a look at how alkenes, so remember that E, we've got the double bond, react. So first thing we're going to look at is combustion, so reacting with oxygen. RXN is a nice shorthand way of writing the word reaction with oxygen. And actually they burn with a smoky flame. And that flame is generally yellower than with our alkanes. And more often than not, they undergo incomplete combustion. Not always, but often. And because of this incomplete combustion, generally the alkenes are going to release less energy per mole, so per like 6.02 times 10 to the 23 molecules of that alkene, than the conjugate or the significantly similar alkane. So if you compare alkane like ethane and an alkene like ethene, the alkane or ethane will release more energy than the alkene ethene. So an example of the complete combustion, as we've seen before, complete combustion is producing carbon dioxide and water. And you just have to balance the equation out using oxygen. Remember, it's a diatomic molecule. Please don't just leave a single O floating about. Now, as well as combustion, we're going to look at something called an addition reaction. Now, in our alkenes, we know, and we'll draw ethene for example, we have got that carbon-carbon double bond, okay? And that carbon-carbon double bond means that if we think about the overlapping of electron shells, like in covalent bonding, as these molecules would, a double bond is where we've got two pairs of electrons that are sharing. Okay, and that carbon-carbon double bond, because of that two pairs of electrons being shared, we can say that it is electron dense. Now, where areas in molecules are electron dense, they're more reactive. And actually, that carbon-carbon double bond is super reactive. That super reactive carbon-carbon double bond can then break and open up. And sort of a bit like if you clasp your hands together by hooking your fingers together, that's like a double bond. And then what happens is that other molecules that want to react with that double bond come and sort of float near it, and that double bond breaks and it opens up. And that's called an addition reaction. Now, if that doesn't make sense, I will show you on the next slide what I mean. Fear not, don't panic, it's going to be fine. Okay, so here's the example of an addition reaction. I've got that ethene that I drew on the previous slide, and I'm going to have some bromine. So bromine floats around as Br2, and what I end up with is that bromine as a reactive species, as a reactive molecule, floating around close to that double bond. And as we've said, what happens is that double bond splits. Okay, so it sort of opens up. We can draw it like this in terms of chemistry. And what happens when that double bond splits is that it turns into a single bond between the carbons. So we've lost the carbon-carbon double bond, and we've produced a carbon-carbon single bond. But we've also added in bromine. So what that carbon-carbon double bond has done has almost become an extra arm. Okay, so the bromine is added, and it only gets added around the double bond. Oh, I've written added twice. Okay, but you get my drift. Now, this addition reaction is exactly the same if you were to use potentially something like iodine. So if you had two I's and ethene, again, C, I'm just going to do ugly H's. That's going to react, it's going to open up that double bond, and it's going to add the iodines in to the end of my molecules. Now, I just want to quickly point out this naming. So what we've done is we've taken ethene, E-N-E, that double bond, that alkene, and we've added two lots of bromine to it. So di means two, bromo from the bromine, and this last bit is really important. It's not ethene anymore. Because it hasn't got that double bond, it's ethane. So two carbons, still a hydrocarbon, and we can check that it's all drawn structurally correct by just counting how many bonds each of those hydrocarbons have. So, or each of those carbons, sorry, not hydrocarbons. Okay, so you can see each of those carbon molecules has got 4 different bonds around it, and therefore it is a saturated hydrocarbon dibromoethane. Now what we can do is we can use the fact that alkenes react with bromine water to test for the presence of alkanes or alkenes. Because realistically, they both look the same, an alkane and alkene in solution. They're both going to be clear. So what we do is we put something called bromine water, which is Br2, in an aqueous solution. And with an alkene, we know that we're going to get that addition reaction. And that's going to add the bromine into the hydrocarbon. So bromine is integrated, or you can say added in. And what we form is something called a halo for the halogen alkane. Okay, and that's all because of the fact that we have got that addition reaction happening, that double bond breaking up and opening, and therefore that bromine water that was initially orange is now colourless. Okay, whereas with alkanes, because they haven't got that carbon-carbon double bond, they can't undergo addition, so they can't add the bromine into their structure, and therefore that bromine water remains orange. So now it's time, I know this looks an absolute mess, I'm sorry, to do a little summary. So could you please have a go at filling out this table comparing alkanes and alkenes, and I've picked ethane and ethene. So you need to draw me a diagram of their structure, decide whether they're an alkane or an alkene, what they're made of, what types of bond they've got between them, whether they react with bromine water, and if so, what's the result? Are they saturated or unsaturated, and what is the general formula for that type of molecule? So you can pause here, spend about 5 minutes again comparing the two structures, and play again when you are ready. Now structurally, they look very similar, but remember ethene has got that carbon-carbon double bond. So ethane is an alkane, it contains carbon and hydrogen, only single carbon-carbon bonds. Bromine water stays orange, it is a saturated molecule, and the general formula for those alkanes are CnH2n plus 2, whereas ethene is an alkene, carbon and hydrogen again, so they're both hydrocarbons, but alkenes have got carbon-carbon double bonds as well as single bonds in bigger molecules, and because of that addition reaction, bromine water will go from orange to colourless. Now these molecules, these alkenes, are unsaturated, and the general formula is CnH2n. If you didn't understand any of that, pause the video here, go back to the section that you've missed, maybe messed up a little bit, have a look at other videos on YouTube, ask me, ask your actual chemistry teacher, not me, and we'll sort it out. So now we're going to take a look at some more addition reactions of alkenes with halogens. So I'm going to do the first one for you, and then I'd like you guys to have a go at writing these out. So as you can see, I have got propene here, so C3H6, reacting with bromine, so Br2, and I know that that is going to produce a single product, so C3H6Br2, and that is di for 2, bromo for the bromine, and then it's propane, because we've got that single bond. Now have a go at writing out the chemical equations and then naming the product for each of them. So pause and then play again when you're ready to go through the answers. So the first one, I have got butene. Remember, it's that double bond plus bromine, and that is going to give me dibromo for the bromine, butane, which in chemical formulae is C4H8Br2. Then I have got ethene, and chlorine, and that's going to give me dichloro for the chlorine, ethane. And again, I'm changing that, so C to H4Cl2. And then finally, I have got propene plus iodine, gives me a really annoyingly named molecule, diiodo for the iodine, propane. And remember, it's AneC3H6I2. We can also add hydrogen in an addition reaction, because hydrogen is still a gaseous molecule, and those highly reactive carbon-carbon double bonds can react with more than just the halogens. So if we're adding hydrogen to a molecule, we say it's hydrogenation, addition of hydrogen, and we know, or we should do at least, that hydrogen floats around as a diatomic gas, H2. Now, hydrogenation of alkenes to alkanes has to be done at 60 degrees and in the presence of a nickel catalyst, and the chemical symbol for nickel is Ni. And what that addition of hydrogen does is it makes our double bond split in the same way that adding a halogen does, and it produces a very simple alkane. Now we've got to consider why we might want to go from an unsaturated alkene to a saturated alkane, when in all of the previous bits of the lesson we've been speaking about going from an alkane, a big long chain alkane, and cracking it down into an alkene. So pause now and do a little bit of research on your own and find out what the advantages and disadvantages are for turning an alkene into an alkane. So again, pause and we'll play again when you're ready. So the first advantage is the fact that breaking that carbon-carbon double bond straightens the molecules. The carbon-carbon double bond actually enables some bending into our molecules. And if we break that up into the carbon-carbon single bonds, then we're going to get a straightening of that structure. Now what that means is that the molecules can pack a little bit more tightly together, and it means that they're better in terms of aligning their structures, and that gives other physical properties that we're not going to go into now. We're going to result in an increased melting point, okay, due to, in part, that straightening, and that in turn means that the chains can sort of link together a little bit better, not bind, but sort of interact with each other. And that overall gives us an increased melting point. It takes a little bit more energy to break those chains apart. And this is used in things like margarine. So let's take a look at an example of this. If I've got propene and it's got 2 hydrogens here, and then 1 here, and then 3 over here. If I've got a couple of those molecules, they are not going to be able to align nicely over each other, okay? Because that double bond means that we've got a sort of kinked structure over on the right-hand side. That's not very useful. Whereas if I've got propane, so I've hydrogenated my structure, I've added those 2 hydrogen molecules in there, I've used 60 degrees and a nickel catalyst, and now I've got propane, my chains are actually much more better suited to aligning with each other. And this hydrogenation of the alkenes means that the alkanes themselves can be used in a... Sorry, there's a hydrogen there, I just can't see it because my little board is in the way, hold on. Can be used in a variety of ways that the original alkene couldn't. And what we've actually got by ensuring that the chains are sort of linked is that margarine now becomes spreadable because those hydrocarbons are able to slide over each other a little bit more easily. They're not locked in together. Now, our molecules of ethene and other alkenes can actually undergo another type of addition reaction, and this is where we're adding in water. Okay, so we're going to take the example of ethene reacting with water, and this makes something called ethanol. Okay, so OL is the suffix, so the bit that goes on the end of the words for alcohols. And notice that the eth or eth stays the same. And it's made in a reaction called hydration. And this is when we're going to add water to our molecules. In hydration reactions, we have to do it with a phosphoric acid catalyst, and we need high temperatures and high pressures because this is quite a complicated reaction for molecules to undertake. As you can see in this reaction, the double bond has been broken again. Okay, so that double bond is now nice and open. We're going to add one hydrogen. I'm just going to put a little star next to it onto the end chain carbon. And then we're going to add this OH group as a functional group. Okay, and when we say functional group, we're talking about groups of molecules that are found within other molecules to give them their properties. Okay, and the OH functional group is found in alcohols. That's not to say it doesn't occur in other molecules. We're going to have a look in a second at something called a carboxylic acid. But by itself, with no other molecules, the OH group is for alcohols. Now, this addition reaction, this hydration reaction, is reversible. So what we can actually get is ethene, C2H4, reacting with water. And we're going to use the reversible reaction arrows to show the production of ethanol. Now, what we can have happening is the forward reaction, producing ethanol, but also the reaction going in the reverse direction. And that's going to produce steam, which remember is just water vapour or H2O and the gaseous state. That steam with the unreacted ethene or the ethene produced by the backwards reaction, so I'll just label it on there for you, backwards, can be recycled, so it can get passed over that phosphoric acid catalyst and the high temperatures and pressures again. Okay, and we can try and keep producing as much ethanol as possible. Now, covalent bonding wise, you can see here that we've got lots of bonding groups going on, and it's not entirely drawn in. So I'm just going to finish this off. I'm going to use crosses for the electrons from this first carbon, and then I'm going to use blue dots for the electrons from this second carbon, and then I'm going to use orange crosses for the electrons on that third molecule, the oxygen in that chain. Now we know that oxygen is in group 6, and I've used 2 electrons already there for that oxygen. And oxygen has got 2 pairs of electrons that are just by themselves on the outside of its rings. Now, if you're not too sure about the structure, just double check that each of the molecules has got the right number of bonds. So each carbon has got 4, yep. The oxygen has got 8 electrons, yep, and hydrogens have all got 2, absolutely fine. Now, the production of ethanol is really important. Okay, ethanol is used in lots and lots of everyday products, not just alcohol for when adults like a drink. Absolutely not. And we can do it in 2 different ways. We can hydrate ethene, or we can undergo the fermentation reaction of glucose. Now, the hydration of ethene is normally used if we've got excess crude oil, and then we're going to use fermentation of glucose if we're trying to produce alcohol for consumption. So fermentation occurs like this. I've got my plant, maybe I've got some sugar beet or something like that, and I'm going to extract the sugar from it, and I have to use the sugar glucose. When it comes to A level, you guys will find out that there's lots more sugars than just glucose. But what I'm going to do is I'm going to take that glucose and I'm going to add yeast to it. And yeast is a biological organism, it's a fungus, and the enzymes in the yeast are going to act as a catalyst. Okay, that's going to reduce the activation energy and it's going to increase the speed of my reaction. And then it undergoes fermentation, which is a type of anaerobic respiration in those yeasts. So we do it in low oxygen conditions. We do it at room temperature, around 30 to 40 degrees, and we're releasing carbon dioxide. We're going to try and get that gas out because we don't need that to build up. Fermentation is normally done as well in something called a batch process, which is where I've got a certain amount of crop, I'm going to ferment it, and then I'm going to tap it off. I'm not going to keep trying to add more crops to my system and then remove a little bit of product as I go. I'm going to do it all at once in a batch, and then I'm going to take it out, and I'll start again from the very beginning of extracting the sugar, adding the yeast, going through. Okay, you know that we like when they produce wines and things like that, they do them in different years, and that's because of the batch processing. So they don't do a continuous supply of wines and things like that. They do it a certain few months of the year. Equation wise, we have got this down at the bottom. So we've got aqueous glucose, or glucose in solution, and I'm just going to write it out better for you because that's ugly, and that just ferments. Notice we've got no oxygen going in because I've said it's anaerobic, to produce ethanol. And what they've done here is they've written it out in the structural formula, and what that means is that it's how you would draw the structure if you were to have to draw like the C's and the lines and the bonds. So it'd be like CH3 and then a CH2 and then an OH group, or you can group them all together to form 2 lots of C2H5OH and 2 lots of carbon dioxide. Notice that alcohol is still in an aqueous solution, but the carbon dioxide is left and released as a gas. As a reminder, if we're producing gas molecules and we're not keeping them in our closed system, then they're going to get a loss of mass because these gases are going to be taken out into the atmosphere. Advantages of using this glucose fermentation process is that the sugar is renewable, and actually the batch processing means that we can use equipment over and over again, but it's quite cheap as well because it doesn't need to be able to last all year. And it's slightly more carbon neutral. We don't need a lot of energy input. However, it's very slow. Alcohols can take months, if not years, to be produced. And actually, because we've got that glucose solution with the yeast and stuff, we've got to do a little bit more processing, like distilling the solution to get out the alcohol. Now, because it's a batch process as well, in the time that we're producing the alcohols, there's going to be a lot of work that needs to be done, a high labour cost, so the business is going to have to pay workers and lots of energy for that specific amount of time. And we've got to think as well about the limit of the strength of the alcohol that we can make. So I can never, using this method, produce 100% alcohol out of my reaction. And this is because of a few reasons. Firstly, there's no market for 100% proof alcohol. No one wants to ruin their insides. But mainly, it's because the alcohol is toxic to the yeast. And we say that this is an endpoint limited reaction. So producing the alcohol, or over a certain percentage of alcohol, then the yeast die. And that in turn is going to result in a reduced production of alcohol at a later date. We don't want to kill yeasts unnecessarily. They haven't done anything to us. They're being quite useful. We need to use that alcohol for lots of different things. So we keep the production of alcohol low, and then this is the reason for that batch processing. I can control it, and when it gets to the certain amount of alcohol production percentage that I want, I can stop the process, I can do all the filtering and stuff, and then I've got my product. So we don't... However, as we well know, there is the other alternative, which is the hydration of ethene. So hydration, we're talking about adding water to our alkene. But I've got to get my alkene somehow, so I'm going to firstly extract it from crude oil, and then I'm going to undergo fractional distillation and then cracking. So everything that we've spoken about before. I'm then going to hydrate my alkene, ethene, and I'm going to add steam to it in order to do that in the presence of a phosphoric acid catalyst at high temperatures and pressures. And I can do this continuously. Now, the reason I can do this continuously is because in this reaction, Where I've done the cracking, I've only got ethene. And that means that as soon as I mix my ethene solution with water, my only product is ethanol. And that means that I can continuously do this. I can continuously cycle this process around, especially in the hydration chamber or wherever you're doing this reaction. And anything that I remove from that mixture, anything I remove from my product solution, is going to be ethanol. So I don't need to stop, start and worry about killing anything throughout this process. This has got, again, advantages and disadvantages. Now, obviously, the advantage is that it's very, very pure. Okay, and it's very quick as well. It's all you've got to do is pass some steam through it. And most importantly, we've got a very high yield overall. Now, this yield starts at about 5%, but remember, it's a reversible reaction. So we can take that unreacted ethene from the backwards reaction and we can recycle that with steam to continually produce that alcohol that we want. Now, because it's a continuous reaction, doesn't require much monitoring, doesn't require many people to go like, oh, that's ready, take it out. We can just process it and get rid of it. Disadvantages, however, we've got a very high initial cost. Okay, this continuous processing is very, very expensive, and it's also very high energy. Remember, we need the high temperature and the high pressure, and that's going to cost. We've got to have a way to make that pressure as high as it needs to be. As well as this, the ethene that we're using comes from crude oil, which is a non-renewable resource. So we've got to be aware of the environmental implications as well. Now, looking at alcohols, we've got a few physical properties that we need to be aware of, and I know this is a really awful picture. I'm sorry it was imported from PowerPoint. The longer the hydrocarbon, so things like octanol, nonanol, decanol, things like that, the stronger the intermolecular forces are. Okay, the longer the chains, they're going to hold on to each other tighter. And as a result, they're going to have a much higher boiling point. As well as this, longer hydrocarbons are less soluble in water. They just sort of float around on top. You get a little slick on the top of your solution. And they've got quite a low density as a result. They don't integrate with each other very well. We've also got to consider the reactions of things like alcohols with sodium. So alcohols themselves allow sodium to sink through it. So sodium is more dense. Sodium, the metal Na. And it doesn't melt. So instead, the reaction of sodium with alcohols just gives off a slow stream of hydrogen gas. Whereas alkanes don't react with sodium. And we haven't covered that yet, but that's a little fact that we need to know. Now, we've got a couple more groups to look at. These are the first. The carboxylic acids are another type of hydrocarbon molecule. So they're carbon and hydrogen based, but they've got something called the COO group, or the carboxylic acid group. I'm going to call it the carboxyl group. And that is a hydrocarbon chain sort of over to the left of the molecule, and then that COO at the side. The general formula for these carboxylic acids is CnH2n plus 1 COOH. And you can see here we've got a very interesting functional group. So this bit over here, we've got a carbon-oxygen double bond, and we've also got a carbon-oxygen bond, and then we've got our hydroxyl group from the alcohols. And we need to be aware of how we name them. So have a go at doing a little bit of matching using what we've done over the past bajillion slides or so. It's not been long or anything. I don't even know how long this video is at this point. To matchy what you would call a carboxylic acid with each of those carbon chains on the left hand side. So pause and then play again when you're ready. Hopefully it should have been quite simple. We are just following exactly the same rules that we have used for the entire rest of the lesson. Eth is for 2, so ethanoic acid is our 2 carbons, and that is actually vinegar. Then we've got propanoic acid, 3 carbons, butanoic acid, 4 carbons, and pentanoic acid for 5 carbons, although you're only expected to be able to name up to 4 carbons. Now it's your turn to have a go at naming this molecule. Have a look at it, see if you can figure out what it is, count the carbons. Nice and easy, this shows ethanoic acid. Now carboxylic acids as solutions have got a few properties, and it's just here on this horrible bubble. The bubble shouldn't be there, can't be bothered to figure out the animations. So what these carboxylic acids do in terms of their properties is they form acidic solutions when they're in an aqueous solution, so if they're dissolved in water. So that means that my pH is going to be less than 7, and it's be maybe slightly more yellow in colour with universal indicator. I'm just going to write UI. Now it's less acidic than nitric and hydrochloric acid, so it's not really acidic, it's just slightly acidic. And because it's only slightly acidic, it means that generally these are found in food substances. As I've already said, ethanoic acid is vinegar, and actually they've got quite unpleasant smells and tastes. I'm not going to go and do a Beyonce and drink some apple cider vinegar. It's up to you if you do, I'm not going to judge you, but you know, what is going on with your life. In terms of boiling points and flammability, they've got higher boiling points than water because they've got those really big intermolecular forces. They're going to interact with each other and want to be sort of holding on to each other, and they are not flammable. You cannot burn vinegar. So the carboxylic acids, like everything else that we've spoken about today, the alkanes, the alkenes, the alcohols, have got reactions that they undergo with different substances. So carboxylic acids act very similarly to any other acid that we've spoken about over the course of your GCSE. So a carboxylic acid reacting with a metal, something like sodium, gives us a salt and hydrogen gas. So we're going to see bubbles, the sciencey word for which is effervescence. Carboxylic acids react with carbonates, so a metal carbonate, to form a salt and water and carbon dioxide. And again, you're going to get gas bubbles normally produced. Be careful with this because they could use this as an excuse to bring in other topics. So you can test for that carbon dioxide using lime water, and that's going to go cloudy. And then finally, if we get a carboxylic acid reacting with an alkali, then we're going to get a salt and water in a neutralization reaction. So have a go at using those equations, those general equations from the previous slide, to figure out what the products of each of these reactions are. So you can pause here. Hopefully it shouldn't take too long. As you can see, for the first one where I've got a salt being produced, it's got a bit of a funny name. So ethanoic acid and sodium carbonate form sodium, so I'm going to use that metal name. And then ethan from the carboxylic acid. And then I end it with the ATE that comes from the carbonate. Okay, so sodium ethanoate and water and carbon dioxide is what happens when ethanoic acid reacts with sodium carbonate. Pause now, play again when you're ready to go through the answers. So for the second one, methanoic acid and calcium carbonate, very similar to the top one. We're going to have calcium methanoate plus water plus carbon dioxide. I'm just going to write carb diox because I'm lazy. If I react ethanoic acid with sodium, then I am going to end up with sodium ethanoate again. And hydrogen. If If I'm reacting propanoic acid with magnesium, I'm going to get magnesium propanoate and hydrogen. Ethanoic acid plus sodium hydroxide gives me sodium ethanoate and water. I'll write water because I'm doing the word equations. And then finally, butanoic acid and potassium hydroxide gives me potassium butanoate plus water. So now it's your turn to have a go. Got a couple of questions, one of them easy, one of them not so easy. Name that big molecule and then give the equation for propanoic acid reacting with potassium hydroxide. Can you do it as a word equation and then with the displayed chemical formula? Let's pause and then play again in a couple of minutes when you're done. Now for this first question, you should have started by counting up the carbons. So I know that I've got 1, 2, 3, 4, 5, 6 carbons, and that 6th carbon comes from the Cu group. So it's hexanoic acid. That Cu group implies that I'm looking at a carboxylic acid, and therefore that's what I should have basically been doing. And then the equation for propanoic acid with potassium hydroxide, acid plus base gives you the salt plus water. Propanoic acid, potassium hydroxide gives potassium propanoate and water. And in our equation, it looks like this. As you can see, aqueous because we are in solution. And then the only liquid that you're producing is that water from the neutralization reaction. Now, carboxylic acids are able to, annoyingly, react with alcohols. So you thought all of this time that we were just learning things for the sake of it. Nah, we're learning them so we can make something better. Carboxylic acids reacting with alcohols forms something called an ester. Now this is a reversible reaction and it's producing water as well as the ester. So you can see here that we've got the acid and the alcohol making that ester and water. But it can go both ways. So please don't forget that it's not a single forward reaction and then loads of waste product and that forwards, backwards. And in order to drive the forward reaction, so to make the carboxylic acid and alcohol produce more esters than the return reaction, we use sulfuric acid. Okay, so that's a really strong acid, a low pH, pH 1, pH 2, to drive that reaction, to reduce the activation energy, to make that happen faster. Now, esters have got a really annoying name, and that's what we've been speaking about in all of our salt products when we've been talking about them. The first part of an ester's name comes from the alcohol. So if I'm using propanol, for example, then it would be prop and then YL. So YL is to do with the ester. And then I'm using the acid for the second part of my name. So ethanoic acid gives me an ethanoate. And that's for our ester as well. Okay, so propyl ethanoate is produced from propanol and ethanoic acid. Now for each of these, could you please have a go at telling me the alcohol and the carboxylic acid that makes up each of them? If you're not too sure, you can see from the structures which part of the molecule is the carboxylic acid part and then which part is the alcohol part. Okay, remember the carboxylic acid is going to have that COO bond. So pause, tell me the alcohol and then the carboxylic acid that goes with each. So for the first one, I've given you ethyl propanoate. You should have recognised that the alcohol is ethanol, just there. And then the carboxylic acid is propanoic acid. For propyl methanoate, we do the alcohol is propanol. It's that little chain, and then the carboxylic acid is methanoic. I'm just going to write methanoic A because I can't bother to write acid. For the methyl butanoate alcohol is methanol. Again, just in that little chain. And then the carboxylic acid is butanoic acid. And then finally for propyl ethanoate, the alcohol is propanol. And then the carboxylic acid is ethanoic acid. So again, just as a recap, the alcohol gives the first part of the name and is found on the chain attached to the O. And if you're not sure what it is, count the carbons. There's 3 carbons. It's going to be propanol. And then the carboxylic acid is literally just the rest of it. So methanoic acid gives me the second part of the name, and it's the bit that's attached to that C double bond O group. We're counting the carbons again. There's only 1 carbon from that bit. Meth. Or meth. I realise that me just saying meth is not very helpful. Alright, we're an hour and 20 in. I'm bored of my voice. You're bored of my voice. We've got 14 more slides left, I promise, and then I will leave you alone. But you asked for this, so don't moan at me. We're going to follow up with looking at the structure of esters, with the properties of esters, and then we're going to have a look at polyesters, and then we're going to have a look at some polymers, and then we're done. It's 14 more slides to go. I'll be as quick as I can, while being as thorough as I can, because no one wants a half job. So the properties of esters and the way they behave is that they're volatile, and that means that they evaporate quite easily. They're often found as gases. And because they're often found as gases, we use them a lot in industry to give things aromas, because they've got quite sweet and fruity smells. If you choose to do A-level chemistry, you'll be able to make some esters, things like pear drop smell. I can't remember for the life of me what that ester is called, but you'll have to believe me. That's all you need to know about properties of esters, by the way. I'm just waffling to fill some time. As previously mentioned, bored of my own voice, so it's time for you to do something now. Have a go at these questions, please. Looking at the reactions of carboxylic acids, and then having a go at the extension question at the bottom. Explain why propanoic acid is only described as a weak acid. Should take you a few minutes, maybe 2 for the top one, and then maybe another 2 for the bottom. So pause and play again when you're ready to go through the answers. So first question, carboxylic acids react with carbonates, so metal carbonates, to give carbon dioxide gas. Carboxylic acids also react with alcohols to form esters and water. This reversible reaction is catalyzed by sulfuric acid, that strongly acidic acid, and the esters formed are volatile compounds used in flavourings and perfumes. For the bottom question though, this relied on your knowledge from lessons on acid-base chemistry that you've done previously. Propanoic acid is only described as a weak acid because it doesn't fully dissociate, or it doesn't fully ionize in aqueous solution. And as a result, it doesn't produce a high concentration of hydrogen ions in solution. And if you're not too sure about these strong and weak acids, I suggest you go back and find either another video or look over your notes from when you've done acid-base chemistry before in a previous module. Now we're coming to the end. You'll be thankful. 11 slides left. First one we're going to look at is the process of polymerization. So addition polymerization is where we add lots and lots of alkene molecules, so we're going back to the alkenes, together. And as you can see here, just in case you're not sure what a polymer is, that's a horrible picture. Lots of individual daisy chains would be considered the monomers, like monobrow or monocle, a single lens. And they join together to form a polymer. Poly means more than 2. Okay, and they're all attached together to produce a bigger molecule. Now for this polymerization reaction, we generally need a high pressure and temperature, so it's going to be a anything to be doing. It's going to be expensive. It's going to cost a lot of money for the business to do. And generally an initiator, something to kick off the reaction, maybe reduce the activation energy, perhaps something like a catalyst. And we can see in this diagram that I've just got lots and lots of ethene alkene molecules at the top. Okay, so C2H4, 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 C2H4. And actually, I don't want to have loads of ethene molecules. I want to stick them all together. So what I do is I open up the double bond. I use my catalyst perhaps. I use my high temperature, high pressure, and I break open all of those double bonds. And what happens is that all of those double bonds that are now broken can join up with each other and they form a long polymer. But this is a bit faffy to draw, isn't it? Because I don't want to sit in an exam drawing like 6 C2H4s around. So instead is we simplify it to this. So I can have ethene drawn once and I can put an N at the beginning of it. And that N just signifies a large number of those individual monomers. And ethene could be something else like propene, butene, whatever. But what I do then to show that it's become a polymer is I stick some square brackets around. And they have to be square, not curved. We're not like making a little point in something. I've broken that double bond. So that double bond is now at the sides. And then I put N at the bottom. And that N just symbolises and is exactly the same number as the N that I've put at the beginning. So if you're not sure, I'm going to show you what we do if we've got propene, for example, and if I want to make polypropene. So I've got C, double bond C, and then we've got 3 hydrogens on that one. Just got 1 hydrogen there and a couple of hydrogens there. I stick an N at the front of it. I'm going to have my reaction arrow. I know it's going to be at high temperature and high pressure. And then what happens is that double bond gets broken. So I know I'm going to be using square brackets like this. And actually what I'm going to do is I'm going to change the shape of my molecule. Okay, it's still the same molecule. I've just made it bend a little bit so I can show that splitting. So now I've got polypropene there. And if you're not sure still, ask. Send me an email, ask me a question, look for another video, and let me know if you're struggling. Addition polymerization is quite easy to name. You just generally stick the word poly on the front of it. Okay, so polyethene is made from ethene, lots of them stuck together. Polypropene, we've seen, is lots of propene stuck together, and so on and so forth. Now, generally speaking, addition polymers are great. They provide a lot more uses than the initial monomer themselves. They're a little bit more useful in terms of their properties as well. But they're really difficult to dispose of. You can't break them down easily because the bonds between the atoms are really, really strong. Now, because of this, they are non-biodegradable. So there's lots of government policy that's now saying reduce the amount of polyesters and polymers that you're producing because we can't break them down. So we need to find ways to recycle them. We can also have another type of polymer produced through a condensation reaction. And this is going to occur when monomers have 2 differing functional groups. Not necessarily 2 differing functional groups on the same molecule, but between the molecules they're going to have different groups. Now we say it's a condensation reaction because we lose water throughout the reaction and we form a specific type of bond between those 2 monomers. Now polymers are generally produced via condensation when a molecule has 2 of the same functional group on each monomer. So we can generally just draw a box for a hydrocarbon chain, and then we can put our functional groups at the side. Okay, so you can see here that I've got two carboxylic acid groups, and that is a dioic acid. Okay, so a something dioic acid depending on the length of the hydrocarbons in the chain. Likewise, if I've got two OH groups, then my molecule is called a diol. Okay, di meaning two. So have a go at drawing out ethane diol and hexane dioic acid, thinking about what I've just said. Have a look at those molecules. How do you think they'll bond? So if I've got ethane diol, I've got C, C, and I know that I've got an OH group there and an OH group there. I'm just drawing the OH this way round because I did A-level chemistry. I know that the carbon binds to the oxygen, not the hydrogen, but it's completely fine for now to write it like that as well. I'm just going to rub that out though because it looks ugly, it looks messy. And then I've got hexane dioic acid. So I know I'm going to have 6 carbons in my chain. I'm going to have hydrogens knocking off of each of those in the middle. And then I know that because it's a dioic acid, it's going to have 2 lots of that carboxylic acid group. Okay, so the way that these bond is really, really interesting. What they do is they cause the elimination of a water molecule. And I'm going to show you that on the next slide. So what we can see here is our carboxylic acid, or our dicarboxylic acid, reacts with the diol, and we actually get removal, if we ignore this N for a second, of a water molecule. So that H2O, we're removing an OH from there and a H from that HO group on the alcohol to produce water. And that forms something called a polyester, because we produced an ester with that carboxylic acid and a diol, but this can happen over and over and over and over again, giving us that polyester. So we're just going to quickly map where each of these structures are in the reactants and then the products, just so we know what we're looking at. So this first C double bond O is there. The second C double bond O is there. We've removed that H2O from the OH group on both the dicarboxylic acid and the diol, and we've got that lone oxygen floating around, which is there. And then that oxygen as well will undergo another reaction on the next carboxylic acid. So if I zoom out quickly, we've got to imagine that there's another carboxylic acid here. Okay, and again, we're going to get removal of that group. And then that's going to produce a next polyester. Now, polymers naturally occur in things like DNA, and you should know from biology that DNA is made of nucleotides consisting of a sugar, which is deoxyribose, a phosphate group, and a nitrogenous base, proteins, which are made from amino acids, and then things like starch and cellulose, which are both made from glucose bonded in different ways. And it's the bonding between those individual monomers that determines the shape of the polymer. And you'll be pleased to know, if you pick A-level biology, we spend like the first 4 weeks looking at the structures of molecules. It's a real thrill a minute. But to finish off, we're going to have a look at how proteins are formed. So here we've got an amino acid. This is glycine. It's a very simple amino acid. It's got an R group of H, just a single hydrogen. Now, these amino acids bind to each other. And we can see here that in our amino acid structure, we've got 2 different functional groups. So over on the left-hand side, we've got what we called the amine group, or the basic group. And over on the right-hand side, we've got this Cu group, which we know is a carboxyl group. We've seen this already. Okay, so if we think about how they're going to react, I'm just going to draw 2 of these monomers together. So a monomer is just a single subunit. Okay, Okay, so we've got N's and H's and we've got a C. And this is where biology and chemistry really combine. Now we can see here already that we know we're undergoing a condensation reaction because we're talking about condensation polymers. And if we're talking about condensation, we're going to remove water. And that removal of water has to occur between functional groups. And what I mean by that is that it's no good saying, oh, okay, I'm just going to remove water from here. Because that's not possible. That's not science. That won't work. So instead what we've got to do is we've got to look at a region where we can remove two H's and an O from a molecule and not disrupt the structure too much. And the easiest way to do it is by taking out these ones. Okay, so what we've got is the loss of water, and then we've got H, N, H, C, H, H, still from all over here. And then we've got this section changing. So we've got C, double bond O, N, H. So we've lost the rest of that structure to the water, and we're left with C, H, H, C, double bond O, H. And this bit in the middle, it's called a peptide bond. That's what makes proteins. That's it, thankfully, for topic 7. It's a brief overview of everything, but it's covered in enough detail that this should see you right through the GCSE. I hope you found it useful. Please don't ask me to make any again because this has spent far too much of my free time doing this. But yeah, if it helps, then I'm pleased. Let me know if you need any help with anything else. Obviously, I mean it, but also don't because I'm not a chemistry teacher. And yeah, see you later. Bye.